And set up for current slide. And before we get going, let's just go over end of the term stuff. Now, there's a few things going on that I had not anticipated or scheduled for, but they're going to be happening. First, today, this is the day you've been dreading all term long, the last day of class. Get over it. Okay. There's okay. We meet today, go till 10:45. Then at 10:45, as usual, my office hours start. But today I've got an eye appointment right across the street here at UAB West, and so I'm going to have to leave campus between 2 and 2:15 to get over there for my 2:30 appointment. Now, the last time I thought, well, I'll just zip in, zip out. It's just going to be a check, because I had a cataract removed. And I sat there for 2 hours before they even called my name. So I don't know how long it'll be. So anyway, don't count on me being back, because I have to leave here no later than about 4:15 to get over to the Birmingham East Campus for my physics class that starts at 5. So unless they're really quick, which I doubt if they will be, I won't be back here very much after 2:15. I'll be here for a little bit to pack up and leave, but that's about all. Unless they really hustle, and if they do, then I might be back for a few half hour, 45 minutes for office hours. Don't bank on it. Okay. And like you said, anything you have, you can slide under my door. Now, that's today. And then I'm on Birmingham East Campus from 5, a little before 5, hopefully, until after 6:30. So I'm usually there between 6:30 and close to 7 o'clock, just packing up and getting checked out. Sometimes students have questions and stuff like that. So you can catch me there if that's convenient to you. All right, tomorrow, Wednesday, no classes, which is quite different from most Mondays and Wednesdays, because I'm usually in class from 8:30 to 5:30 with 2 5-minute breaks, and that's all. I mean, it's usually really packed on Monday and Wednesday. But tomorrow's the first day of finals, and so I'll be in my office most of the day from 8 o'clock in the morning, unfortunately, until only 12:30, because they've called a meeting, a committee meeting, tomorrow afternoon at 1 o'clock, and the meeting usually goes, it's one that is really long usually goes at least 2 hours. So I don't know what time I'll be back in the office, but I won't be coming back here. I'll be over on the Birmingham West Campus in B122, which is Dr. Pruitt's office suite, but I'm in the copy room behind the secretary's desk. So that's where I'll be, I'm guessing 3 to 6, but whatever time the meeting gets over with until around 6 o'clock. So I won't be coming back here. Okay. Thursday again is a final exam day, and I'll be in the office from 8 in the morning until about 4, because I've got a couple things to do on the way to my last class with the physics, the final exam. So I'm going to be leaving here around 4, I'm guessing, to get over there. But I'll be there from 5 to 6:30. You can come anytime during that time, because there's no class. It's just going to be the final exam time. So you can turn in anything then. Then, and this is something I forgot earlier, we'll be into August by then, and once June and July are over with, we go back to work on Fridays in August. So I'll be on the Birmingham West Campus from 8 in the morning till around 12 noon. After 12 noon, I'm hoping to be out of there. Hoping I'm going to have all my grades in, and hoping they approve my leave so I can take Monday off. So we need to get over to the farm in Georgia to take care of a whole lot of stuff on this weekend between. So I need both weekends and the weekend between to do it. So that's how it's going to be. Everything has to be in. My last time on this campus before I leave permanently for the break will be Thursday afternoon, 4 o'clock. If I haven't received it by Thursday afternoon, 4 o'clock, I'm not going to see it until I get back for fall term. On the Birmingham campus, East Campus, I'll be there till 6:30. on Thursday evening, and West Campus till noon on Friday. So if you leave anything under the door, my office here, after 4 o'clock on Thursday, I won't see it, and people will get incomplete. So don't think that will come over too well. So please get things in. All right, any questions before we get going today? Now, we're in Chapter 4, which is higher order differential equations, and we're in Section 4.4, undetermined coefficients, the superposition approach. Oh, yeah. It hasn't come on? As I pressed the button, I thought it would be on by now, but I guess it didn't press hard enough or something. Pointing now. Okay. We've been talking about how to find your particular solutions, okay? And example 4 on page 146 is showing you a time when it doesn't work, okay? A glitch in the method, okay? Find a particular solution of this differential equation, okay? Y double prime minus 5y prime plus 4y is equal to 8e to the x. Okay? How would you begin a problem like that?
I normally try to get it to 0, automatically 0.
Okay. So you set up what they call the auxiliary equation, or complementary, auxiliary equation, I think is, no, complementary equation. And that would be y double prime minus 5y prime plus 4y equal to 0. The homogeneous case, or homogeneous case. And then what do you do?
I do 0 squared minus 5 times 0 plus 4 plus y.
Okay, I didn't quite follow that. What did you say the first was?
0 squared.
0 squared?
Yes. It's just
But 0 squared is 0.
Yes.
So, huh?
It'll simplify it.
Okay. Okay, 0 squared.
Minus 5 0.
5 times 0
Plus 4.
plus 4?
Yes. And I do parentheses around.
Okay.
Or you.
Oh, wow. I see you pretty well. Missed you yesterday.
Yeah, sorry about that.
Yeah, no problem.
I was out of town this weekend. So
Oh.
We had to move out of my apartment.
Oh.
My landlords asked me if I could move early because they have someone trying to come early.
Oh, I see.
And we.
This is down at Auburn.
Yes, sir. Yeah. And so we went after church, and I thought I could move like a whole bedroom in like 7 hours. We got to like 2 a.m. and we decided to stay in Auburn. So.
Right. Okay.
So I'm sorry about that.
Yeah. Okay. Is that what you meant?
Yes.
Right. Now, what in the world do you do with that?
I'll
Because this equation doesn't make any sense because it says 0 minus 0 plus 4, that would be 4 is equal to 0.
Yes.
And that doesn't.
Yeah, I got it in my notes, sorry.
Yeah.
Are we doing the M stuff?
Yeah. I think instead of zeros, you want M's.
Yes, that's what I'm sorry.
Okay. That's all right. Whoa, my eraser's not erasing. There we go. Okay. And you need one here too. No, you're right. You don't need one there. Okay. You do M squared. That's what I meant to erase was the parentheses. If my eraser would come on, there we go. M squared minus 5M plus 4 is equal to 0. All right. Now what?
Are you trying to be quadratic?
Yeah, well, you tell me.
Let me see. 4 oh, no, you put M minus 4, M minus 1.
M minus 4 times M minus 1. We're factoring. That equal to 0, and that gives you what?
1 and 4.
M is equal to 4, or M is equal to 1. Now, why were you doing the M's anyway? Where are they coming from?
They're coming from y equals e to the mx.
E to the mx. That is your guess, is y is equal to e to the mx. So now we have, and this is called the complementary solution, and that is y is equal to some arbitrary coefficient c1 e to the 4x plus some c2, arbitrary coefficient c2, e to the x. Okay? All right. That took, oh, that's y sub c, which is the complementary solution. Okay? What do you do with your 8e to the x? That solved the homogeneous part, but it didn't do anything with the 8e to the x. Okay. What you do here is guess. Make a logical, hopefully logical, educated, hopefully educated guess of what your particular solution could be. So we'll say y sub p. Now first guess here, probably, and if you look at the bottom of page, if you got a book, oh, you may not have a book, of table 4.4.1, it lists any constant. That won't work for an e to the 8e to the x. Any polynomial, 8e to the x is not a polynomial, so I would skip 2, 3, and 4. Sine, cosine, those won't work. Number 6, some function of e to the some sort of x. Good deal, thank you. All right. And you're going to be getting me the ones for different, I mean, Cal 3.
Yeah.
Right. Okay. Yeah, you don't need it right now, but, you know, just, I didn't want you to forget. Okay. All right. Now, if it's something to do with e to the, some exponential function, let's put it that way. What kind of exponential do you anticipate? Because you're going to be taking a derivative of it and a second derivative of it and itself, and it's supposed to add to 8e to the x.
So we would do 2, right?
2? What do you mean by that?
Like, would we put e to the 2x?
Okay, let's give it a shot. Now, this is called undetermined coefficient, so usually we put capital A, e to the 2x. Okay, let's think about that a moment. If you take a derivative of that, you're going to get, let's go on and do it. We can do it. We can erase easily. Yp prime would be 2a, how do you, e to the 2x. That's not good, is it? And y particular double prime would be 4a e to the 2x. How are you going to ever get any combination of these things, and that's what you would have when you combine these together, to ever give you e to the x? Oh.
I messed up. I was thinking like, we were just going to go until we get a.
Yeah. Okay. Yeah. So, not bad thought, except that you don't need the 2's or the 4's. Okay. Except, is this one going to really do any good? Because you see, one of your complementary solutions is already an e to the x. So therefore, that would just be lumped together, and it's not going to give you, because you see, if you use any combination of e to the x, that's going to give you 0. It won't give you 8e to the x. So what might we do to make it give you an e to the x? How could we adjust our particular solution? It's not something probably you would, yuck, my eraser's not erasing today. Well, it's not even staying on task today. There we go. Okay. What did we do when we had multiple roots? What was our technique then? Like if m was equal to 1 and the other m was equal to 1. But we need two arbitrary coefficients. We put an x in. Well, let's do the same thing here. Since e to the x is not going to work, maybe an x e to the x would work. But that, of course, makes your derivatives a little more challenging. How so? What would be your y prime?
Would it be... So, I just got a question.
Okay.
Is the a constant?
A is a constant, exactly. Undetermined coefficient.
Okay, so it'd just be e to the x minus x e to the x.
Okay.
ax.
Okay.
ax minus ax. ax ex.
Okay. Yeah, you're confusing me, but no, okay. No, good.
Product rule.
Yeah, product rule, that would give you
E to the x.
a e to the x
Minus, or no, plus.
plus
X e x.
a x e to the x. Right? Good. And what about y double prime?
A e to the x.
A e to the x.
Plus a e to the x.
A e to the x.
Plus a x e x.
A x e to the x. All right. So let's combine that to be 2a e to the x plus a x e to the x. Okay. Now, let's plug that into our equation here. Okay. So your y double prime is 2a e to the x plus a x e to the x, right? Yay or nay? Minus 5 times y prime, that would be 5a e to the x, and that's still a minus, 5ax e to the x, okay? And then plus 4 times ax e to the x. And this is supposed to equal, we want it to equal 8e to the x. Okay. Now, let's see if we can make that happen. Well, let's first look at our coefficients for e to the x. There's an e to the x. There's an e to the x. Okay, there are only two terms with just e to the x's in them. And this says that 2a minus 5a is equal to 8. Right?
Yes.
So this would mean, combine like terms,
negative 3a.
negative 3a is equal to 8. Okay, a is equal to negative 8 over 3. You're right. All right. Now, our overall solution then, oh, wait. I like to check it, just to make sure I haven't made a dumb mistake. Let's look at our terms with x e to the x. We have them here, don't we? Okay. Their coefficients are a, should have done this in a different color, minus 5a plus 4a. And what does that equal?
0.
0. Thank you very much, because we don't have an x e to the x term over here, so it better equal 0. That's just a good check to make sure that a works. If you'd have come up with 7a, added those up and got 7a, then 7 times negative 8/3 sure isn't going to give you 0. So you know you made a mistake. So here is your general solution. It's the combination of your characteristic solution or complementary solution and your particular solution, except let's put it in. So this is minus 8/3 x e to the x. Okay? So that would be c1 e to the 4x plus c2 e to the x minus 8/3 x e to the x. All right. Hopefully that's what they got. Particular solution was that. And they didn't do a general solution at all, okay? Shame on them, okay? All right. Now, they do a case 1 here, and I really can't understand why they do a case 1, because nowhere else is there a case 2, okay? So what I'm going to do is a case, okay? No function, the assumed particular solution is a solution of the associated homogeneous differential equation. So that's the issue. Our first guess up here would have been a e to the x. But you see, that matched one of our solutions in the homogeneous case. You can't have that, okay? Now, they list a table here, and neither one of you have books, so let me... Okay, but you don't have one. You can look on? Okay. Here are some trial particular solutions and when you would use them. I may go on and write them anyway, but let's see, in case any of the people listening at home don't have books. Okay, when your g of x is any constant, they put 1, but I'm just going to put any constant, okay? Any constant. Then what would be your particular solution? Yes would be a times a constant, okay? Anytime your g of x would be a polynomial, such as, there's nothing special about the one they picked, 5x plus 7, okay? Then what particular solution would you suggest that we try? ax plus b. It kind of mirrors the g of x, okay? You have to go at least as high in polynomials as you have there, so ax plus b would be a good first guess, okay? Now, again, if you have your complementary solution, okay, if it has a polynomial like ax plus b, don't use that. Then multiply it by another x or do something else to it. But, okay, the odds are it won't. What if your g of x was 3x squared minus 2? What would you suggest your particular solution might be? Hint, it should be a polynomial. Of what degree? No, you better have a squared in there. Okay? Okay, so you do ax squared
2b
Second?
minus 2b.
Okay. You don't need to put any numbers. That's what your A's and B's are going to become your numbers. Second?
Minus
And you don't need to put a minus. You can put plus. Okay. Okay. Here's a problem, Houston. Okay. What happens if you take the derivative of this?
You get
And I'm thinking of this.
you get 2ax.
2ax. Now, once you get that, how are you going to... See, this doesn't have an x term in it. So you're going to need an x term in that, so something adds to 0. And if you don't have anything to add to it, so my suggestion is bx plus c. A full quadratic, not just, don't be limited by the number of terms you have here. Okay? The next one would be, this is just a, arbitrary, x cubed minus x plus 1. What would be your particular solution? Ax cubed plus
bx plus c
squared. You got to include those because you may wind up with one of them in there.
plus c
Plus c
plus
at
x
cx
plus d.
plus d. Perfect, perfect, perfect. Okay? This is on page 146.
We have
146, bottom of the page.
It don't go.
Oh, 4.4.
Sorry.
Yeah. After example 4, before example 5. Got it? All right. Now, what if you had as your g of x sine 4x? What would you guess your particular solution would be? I'll lead off. A sine. Okay. 4x. Done? Well, you're looking, aren't you? Okay. Plus b cosine 4x. Why do you need a cosine in there? I don't have a cosine here. Well, what's the derivative of this?
Cosine.
Cosine. And if you have a derivative in it and you introduce a cosine and you don't have one to cancel it out, you're stuck. It's not going to work. Okay. Second?
Not going to look at the chart anymore.
Not going to what?
The chart.
Charge?
The chart.
Oh, okay. You're not looking. Oh, yeah, right. Okay. Cosine 4x.
Is it going to be a? Would it be sine? I'm going to guess cosine.
It doesn't matter.
Oh, okay. Cosine 4x is b sine 4x.
Yeah, it doesn't matter which one you put with what. You got to put both of them in there because you got to have. When you start taking derivatives, you can't have anything else. You can't introduce a new term that's not covered. Okay.
So the a and the b's don't matter?
It doesn't really matter. The numbers are going to come out whatever. If you chose A sine 4x and B cosine plus B cosine 4x, and then you solved it through, you would have the coefficient for the cosine to be -3 and the one for the sine to be -8/3. Okay. If you did it the other way, you just get the A being one and the B being the other. The one for cosine would still be -3 or whatever it would have been. The math will take care of that. The algebra will take care of it. Calculus will take care of it. It doesn't matter which order you put in, but you'll go and get the same coefficients no matter what order you put in. Okay? How about this one? E to the 5x. A e to the 5x. That's all you need because, see, you take the derivative of e to the 5x and you get e to the 5. Yeah, you get things. 5s, so see, the 5s can be handled by the a's. Okay? But what follows that is going to be e to the 5x. Yeah. Now, if your complementary solution had a sine 4x in it, then that's not going to work. You're going to need a x sine 4x, and probably then an ax cosine 4x too, probably, or bx, I mean, sine 4x. So you see, if one of these forms, if this is your g of x, then you want, and you know, the non-homogeneous case, and then when you do the homogeneous case and the complementary solution, and you get these as one of your possibilities, then you have to inject an x to make sure that it's going to work. Okay? All right, how about if you had this 9x minus 2 e to the 5x. What would be your guess for your particular solution?
AX minus B.
AX minus B, or plus B, you don't need a minus. Yeah.
E to the 5x.
E to the 5x. Unless, of course, your complementary solution had an e to the 5x, and you'd put an extra x in there. Okay? Perfect. Now notice you don't need, with a product, you don't need anything, because you see, you can distribute this, and this would be a 9x e to the 5. E to the 5x minus 2 e to the 5x. Now, let's think back now. What if your complementary solution had an e to the 5x? Then this is not going to help you, okay? And you would need, I think in that case, if you didn't have an x e to the 5x on the complementary side, I think the ax would probably suffice for you. But the bx isn't going to contribute anything if one of your particular solutions was a c 3 e to the 5x. That's not going to be helpful for you. Okay? Now let's do another one. X squared e to the 5x. And there's nothing special about 5, they just use the same one. What would be your particular solution?
AX squared.
AX squared.
Parentheses.
What's that?
AX squared and then close the parentheses.
I wouldn't.
Oh, AX squared plus B X plus C.
Yeah, just like you did up here. If you have a polynomial, you've got to count for every term because, and then this would be times e to the 5x. Okay? Because when you start taking, if you just had that, what's your first derivative?
It's 2AX.
2ax. And if you didn't have something later on to cancel that out, there's no 2ax, there's no x term here. So you have to have all the polynomials included there. Okay? The next one. I'm going to go to the top of the next column, which you don't see. E to the 3x sine 4x. That's your g of x. What would be your first guess for your y particular solution? Okay.
Would it be A sine 4x?
Okay. I would put, it doesn't matter where you put them, but I would put the e, just because it's here, e to the 3x here, but then do a sine 4x plus b. Cosine 4x, perfect, okay? Because if you didn't include that, once you start taking, see, either 3x isn't going to matter because you take a derivative of it, you get e to the 3x. You don't have any trouble with that. It's taking a derivative of sine 4x, you're going to introduce the cosine 4x, and you don't have that in your g of x. So you're going to have it over there so you can, yes?
What if you had sine 4x squared?
Okay, sine squared 4x or sine 4x 4
The
x squared.
The sine is squared.
The sine is squared. I don't believe that is going to be one of your allowed solutions. If you go back, that you can do. Do it numerically is what the answer is. What if you had that? You're stuck. If we go back to 3, nope, we don't go that far back. Where is it here? They have a list of the functions. Yeah. On page 143 in section 4.4, just back a page or two, polynomial functions, exponential functions, sine and or cosine functions. That's it, folks. Not cosine squared, not sine squared, no tangents, no logs. You know, that's the only ones you can allow for this approach. Otherwise, you got to do numerical solution. And see, this is pretty limited. It gives you a lot of possibilities, but it's still pretty limited. No logs, no cosine squared or to any power, no square roots. Those won't work, only polynomials. Okay? Good question. 5x squared sine 4x. What if that was your g of x? What would be your guess for your particular solution?
AX
X squared
plus BX
plus bx
plus C
plus c.
sine 4x.
Yeah.
A sine
Now, that's where the kicker comes. You don't need a coefficient with the sine. You can just do sine 4x. Is that what you're saying? But then you'll need another set of coefficients. I don't have enough room here. They use D, or do they skip D? Yeah, they skip D. They go to E x squared plus fx plus g times the cosine 4x.
I want to say that makes sense, but then again, like, no, that don't make sense.
Okay. It seems like those three coefficients there would have sufficed for you, but I'm trying to think if what you are suggesting might work just as well, and there must be some reason that it doesn't. I just don't know what it is, but I would have been tempted. I think if you were suggesting this, it's what I was thinking. Say to do your E sine times E sine 4x plus F cosine 4x. And then those 5 would have been enough for you. But I guess that there could be a case in which you might need a 6 thing. So this is the one way to do it. Just come up with a whole nother quadratic here with different arbitrary, or what they call undetermined coefficients, and then multiply that by cosine 4x. I think in most of your cases what you said probably would have worked. If you had coefficients for sine and cosine, I think that probably would work. It may be there's rare case that you would need 6 of them rather than 5. I haven't gone into the theory of it enough to know whether really how to answer that. But how about this one? Okay, x e to the 3x cosine 4x. what would you think your first guess for a particular solution might be?
Is the x e?
Okay, you need an undetermined coefficient. That's why they call it that. AX,
Squared.
you don't need a square, because if you put a square in there, you'll never get rid of it. Okay, so you don't want a square there.
AX plus B?
Plus B, yes. You need the constant term, because when you take the derivative of AX, you're going to get an A. And if you don't have anything to get rid of the A, you're stuck with it. Okay? And notice they don't have a constant over here. Okay? That would be times
Cosine.
Well, let's do the
E
to the 3x first. Okay? And then if you wanted to put cosine, you certainly could. Cosine 4x. Then you need,
Sine 4x.
you will need a sine 4x.
AX plus B.
Not AX plus B, other coefficients. CX plus, they like to use E. They don't like to use the but then you'd need an E to the 3x in there as well. But in this case, I can see no reason why not to do this and just do times C cosine 4x plus sine 4x, because then you have 4 arbitrary coefficients. You can rearrange them if necessary. That one you had 6, and doing it the other way would only give you 5. This way, do it either way would give you 4. I don't see any problem with that. They suggest that you do it this way. And I'm not about to complain with them, okay? I might do it some, but not too much, okay? The main thing is that you have enough coefficients for all the possibilities. And there's 4 different possibilities. You need an x term and a constant term for each of your e's and cosines, and e's and sines. So that's why they do it that way. Am I going to give you one that complicated on the test? Bank on it. No, I don't think you'll. I will, okay? I don't think they will either in your homework exercises. I guess it's possible, but maybe not. All right, let's move on to example 5. Too late to ask if you needed me to leave that up any longer, sorry. Determine the form of a particular solution for this one. Y double prime minus 8y prime plus 25y equal 5x cubed e to the minus x minus 7 e to the minus x. All right. Now it says determine the form of a particular solution for that. Okay? Now, I don't like the way they just jump to it and give you a form for the particular solution. You really need to do the complementary function first. Because what if you had an e to the minus x as the m came out being a minus 1? It's not going to, but you do need to check that. Okay? So what would this be? Your complementary, your auxiliary solution?
M squared.
M squared
8m
minus 8m plus 25 equals 0. Now this is for the homogeneous case, homogeneous case. This is to get the complementary solution. And I'll look at that and say, m can't be minus 1. That will not solve that. So as soon as I see that, then I can go back and do what they're going to do. But in my mind, you have to make sure that m equal minus 1 can't be a solution. And you could look at the problem really and tell that it couldn't. But looking at this, m equal minus 1, that would be a 1 plus 8 plus 25, and that's not going to equal 0. So you're safe to go on and do what they suggested. So what is it that you would do to this one?
On the right side.
Say again?
What do we do?
Now this is your g of x. What would be your y particular? That's what we're looking for. What is your y particular to go with this g of x?
What if we say, it would be ax cubed plus
Okay.
bx squared
Ax cubed plus bx squared
plus cx
plus cx
plus d.
plus d. They're not going to use d, but that's all right.
Is that wrong? Times e to the minus x.
Times e to the minus x. Perfect. Now, how you got there, I wasn't sure, but you got it right, okay? Because really the first best idea is to factor out e to the minus x. That's why I put the equal sign there. This would be a 5x cubed minus 7 times e to the minus x. And then that shows you, yeah, you need a cubic polynomial with an undetermined coefficient for every possible term. Now, some of those may turn out being zeros, so you didn't need them all. But you got to get them there in the first place to make sure you don't need them all. And that's why that on that earlier one that we had, where you had 6, and I thought you probably can get by with 5, just in case you can't, do the one with 6, So those are your undetermined coefficients there. Okay, that's the A part. Here's the B part. Any questions on that? I'm going to leave it up there, but that's the, in the book, of course, they don't use D, they use E. Okay, we can live with that. All right. Oh, they did go back and do the complementary solution. I thought they just jumped to it and said, using entry 9 in the table, do this. I said, no, you really got to make sure. But then what they did after they came up with that, they said, note, there's no duplication in the terms of y to the p with the terms of the complementary solution. Now, let's just go back, since they did finally do it, let's do our complementary solution, because I think that's a good idea anyway. What would your m's be here? The possibilities.
Well, we pick quadratic formula, right? I don't see any numbers.
Okay, let's try quadratic formula then. M is equal to 8 plus or minus
square root of 64 minus 100.
Okay. That's 100. That's ugly. Okay. Over
By
2. Okay.
and then we get 8 plus or minus 6i.
Okay, very good. Very good. I can't get my pen back. There we go. Okay, 6i.
5 by 2. Or can we cancel out the 2? We get 4 plus or minus 3i.
Okay.
And then we gotta write it something else.
Second.
And then we write it as something else.
And what would that be?
E to the 4x.
E to the 4x.
Parentheses. Sine. Or
Doesn't really matter.
sine.
Okay, you need your arbitrary coefficients. Yeah.
C1
C1
sine 3x plus C2 cosine.
Yeah, I'm sorry. I get carried away. Cosine 3x. All right. And nothing there contradicts there. If that had come up being e to the minus x out here, yep, you'd have been in trouble here. What you would then do is then interject an x there. And that would then increase that polynomial to be a x fourth plus bx cubed. You know, so you would have put an extra in there in that case, just because of that. But you see, with this being e to the 4x here, and this is e to the minus x here, no contradiction, so that's good. Okay. Excellent. And they don't write down your general solution. Now, and don't worry about the fact in the book they put the cosine first and the sine second. It doesn't matter. They're arbitrary coefficients, you know. C2, C1, what difference does it make? They just don't have to be the same one. Okay. So, let's do the B part. I think we'll go to a new slide then. Got it? Anyone need that any longer? Okay. The B part said y double prime plus 4y equals x cosine x. What do you get here?
M squared plus 4m.
All right, that's where I would go. M squared plus 4. 4, okay.
Equals x.
This is for the 0 equals 0. This is for the homogeneous case or homogeneous case. Equals 0.
There's nothing, I can't see any factors either. So, yeah. Zero minus, okay, so you did square root of 0 plus or minus, or negative 0 plus or minus the square root of 0 minus 16, square root of 16, square root of 16.
Okay. I'm not.
Yes, I agree.
Huh?
I agree.
You agree? Okay.
Alright, that's how to do it by hand.
Yeah. One way is do m squared is equal to minus 4, which you know it can't be. Take a square root of minus 4. M is equal to the square root of minus 4, and that would be plus or minus 2i. Right?
Yes, sir.
Okay. So what?
E to the...
So your y sub c is
Wait,
equal
E
to...
would not exist, though.
Second?
Because it'd be e to the 0,
That's it, which is 1.
1, so it'd just be parentheses, or not even parentheses, sine 2x.
You don't like those
Or
arbitrary...
C1.
Okay, okay. C1
Sine 2x.
Sine 2x plus C2 cosine 2x. That's it. Okay. Now once you see that, then you look up here and say, that's not going to interfere with anything. So what would be your, for this g of x, then what would be your y sub p?
X plus b.
Say again? Bless you. AX plus b
times cosine
times cosine
plus cx
cx
plus e
e
of sine x.
sine x. Perfect. Okay? Again, observe there's no duplication. Here you had sines and cosine, but these are of 2x's, those are of x's, no problem. If this had been a 2x up here, problem. And you have to introduce another x in there. All right. Now, if g of x, now notice all of the g of x's we listed in that table before, except for the polynomials, of course, which are sums and differences, but of the, when you had a polynomial with a sine or a cosine or an exponential or any combination of those, they're all multiplied together. And this is how you do them if they're multiplied. If, however, you had them added rather than multiplied, added or subtracted rather than multiplied, then you have to do something else. If g of x consists of a sum, say, of m terms of the kind listed in the table, okay, and it says then, as in example 3, which we did last time, when you had a 4x minus 5 plus 6x e to the 2x, those are added together, okay? So if you did that, then the assumption of a particular solution is the sum of all of those. So you have y sub p. If you had a series of them, then you could have a y sub p1 plus y sub p2, p2, plus y sub p3, plus dot, 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 up to plus y sub pn, say. Whichever, however many you had, you would have a combination, a superposition of all those, okay? Now, the form rule for case 1, the form of y sub p is a linear combination of all linearly independent functions that are generated by completed repeated differentiation of g of x. So I guess I'll write that down. Form rule for case 1. And here's case 2. I'm missing case 2 at the bottom of the next page. Okay, of this page. So the form rule for case 1. Okay, again, case 1, no function in the assumed particular solution is a function of the associated homogeneous differential equation. Now, example 4 was one that was of the same form, but example 5 wasn't. So for case 1, no function, so I'll write it down now. I thought, here's a case 1, I don't see a case 2, but it was the bottom of the next page. Case 1. Okay. No function in the assumed particular solution those are your y sub p's is the solution of the associated homogeneous differential equation. Of the associated homogeneous differential equation. Got it. Okay? So here's then the form rule for case 1. Okay? The form of y sub p is a linear combination of all linearly independent functions that are generated by repeated differentiations of g of x. Okay, so that's why you need every term in your polynomial, because it says that of all linearly independent functions that are generated by repeated differentiations. If you differentiate an ax squared, you're going to get an x term. So you got to include the x term in your linear independent functions. Now, I'm trying to think back to that other case. Still don't think it would matter that much, but we'd have to see. Okay. Now, here is example 6, which is going to follow that form. Okay. All right to erase?
Yes, sir.
Okay, determine the form of the particular solution for this. Y double prime minus 9y prime plus 14y equal 3x squared minus 5 sine 2x plus 8x e to the 6x. Okay. How would you begin?
M squared
M squared
minus 9m
minus 9m plus 14 equals 0.
M minus 7 and M minus 2. So it would be C1.
Okay, your y complementary solution would be C1
E to the
7x
plus C2
plus C2
E to the 2x.
2x. Okay, that's the 7 and that's the 2. Okay. All right. Now, once I see this and see that, I'm not worried, right? Because nothing here, e to the 7x, e to the 2x, the only e you have up there is 6x. They're not going to interfere at all, ever. So we're not worried about it. So now we worry about our particular solution. That's what they were asking for. What is a particular solution for this g of x?
That one sucks. Yp equals ax squared plus bx plus c.
Okay, that's going to take care of the first one. Y sub p2
ax.
let's go to e.
Ex plus b.
Say again?
Ex plus b.
No, we're taking care of this. We're now going to deal with this one.
E plus b.
Say again? We're dealing with this one. What's that?
E cosine
Okay, yeah, e cosine
2x
2x
plus f sine 2x.
sine 2x. Got it. Okay. And how about the last one? Y sub p3.
G.
Okay, yeah, G, that sounds good.
Gx plus b. Or, I'm sorry, h.
Gx what?
Gx plus bf. H. Plus h.
Second?
Plus h.
Oh, yeah, okay. Okay, you got Gx plus A. Okay, got it.
E to the 6x.
E to the 6x. Good. I was going to do it the other way, gx e to the 6x plus h e to the 6x, but that does it just as well, probably better. Okay? Well, they did the way I was going to do it, but it doesn't matter. Okay?
You really want to go back?
Okay? So now your particular solution, y sub p, is going to be the linear combination of those. Okay? Ax squared plus bx plus c plus e cosine 2x plus f sine 2x plus gx e to the 6x plus h e to the 6x. There's your particular solution. A, B, C, E, F, G, H. 7 undetermined coefficients, okay? And you would have to your yp prime and your yp double prime, work all those out, and then combine, like, terms, the coefficients of them to get the coefficients you need. Might be a little bit of an issue, okay? Now, I can't believe it. They wrote this term multiplied through, and then when they wrote this term, they just interchanged what I did here. And it doesn't matter. Either way works. Okay? Either way works. Okay. And none of those terms conflict with the e to the 7x or e to the 2x. So we're fine. But case 2, okay, would be a function of the assumed particular solution is also a solution of the homogeneous, associated homogeneous or homogeneous differential equation. Notice here it's assumed particular solution. I'm just going to put y sub p. I'm tired of writing particular solution. Is also a solution of the associated homogeneous differential equation. And I'm going to put y sub c. Okay, the complementary solution. Okay, now they mentioned next example is similar to example 4, which was what they called the glitch in the method. So let's do example 7. All right to erase? All right. Find a particular solution of this one. Y double prime minus 2y prime plus y is equal to e to the x.
M squared.
M squared.
Minus 2m plus m.
Plus 1.
Plus 1. Plus 1.
Yeah.
Equals 0.
Equals 0.
Let's see, that would be m minus 1. M minus 1.
Times m minus 1.
C, YC.
Okay. Y sub c is equal to e to the
Wait, C1
c1
to the x plus C2 x to the x.
x e to the x. Okay. Very good. What do you notice though? This form here is just like your geovector. With C1 equal to 1, it would be identically that. And that's arbitrary coefficient, so it could be 1. So, what is your particular solution going to have to be?
It's, is it just, can it be a e to the x?
a for sure, but not e to the x, because that would be the same as this. Okay, what did you do down here? Oh!
AX plus B.
You can't use that one because that'd be the same as this one. Do it again, Sam.
X squared plus BX.
Just multiply by another x. Okay? This won't possibly interfere with either one of those. It's linearly independent from those, right? But if you do your derivatives, you will come out with an e to the x somewhere in there, and you hopefully will get rid of all your others. And on this one, don't do your bx and the c. You don't need that. You just need the extra x's in there. Okay? Extra x's. Okay. All right. Now, let's proceed. How do you determine what a is? So far, they're undetermined coefficients. This time, we're going to determine it. See, the earlier examples, they just said determine the form of the particular solution. Determine the form of the particular solution. This one, they say find a particular solution. Not just the form, let's actually find it. What would that be? How would you proceed? What should you? Yes, absolutely. Yp prime is equal to
2a. 2ax e to the x plus ax squared bx squared e to the x.
All right, very good. Y particular double prime is equal to
2a e to the x plus 2ax e to the x plus 2ax e to the x plus ax squared e to the x.
very good. Got that old product rule down, huh? Equal
4a e to the x plus 6.
You said it, so I wrote it, but it is correct.
No, it's all right. Hold up. 2a e to the x.
Okay, I thought that's what you meant, but
Well, actually, let's restart. Ax squared e to the x.
all right, he's changing everything, isn't he?
Put it
Okay.
in standard form.
Okay, I got you. I got you.
Ax squared e to the x plus 4x e to the x.
AX.
Plus 2 a e to the x.
Okay. All right. Now,
Could we make that simpler?
we could factor out an a e to the x if you wanted to. Let's see what happens if we just do this. This is your yp double prime, so we'll write it down. Ax squared e to the x plus 4ax e to the x plus 2a e to the x minus 2 times y particular prime. So it would be a minus 4, right? Is this skipping too many steps?
No.
Because you seem to like to skip steps freely. Okay, so minus 2 times 2 is minus 4 ax e to the x, then minus 2 ax squared e to the x, right?
Sure.
And then plus a x squared e to the x, And that's supposed to equal e to the x. All right. We need to find an a to make that happen. Where would you begin?
What if you take out e to the x on both sides?
You could. That might make things look a little nicer for you. Okay. E to the x times a x squared plus 4ax plus 2a minus 4ax minus 2ax squared, right?
Wait. Okay. I can just go ahead and tell you it's just going to be 2ax squared.
You had done this one, right? And then that's the next one.
Yeah, but those cancel out, so you're just left with ax squared, 2ax squared, or plus ax squared.
Plus ax squared, okay. Or minus ax squared.
Is it minus?
Well, I don't know. Are you adding these two together?
Yeah, but I'm saying like you can just go ahead and cancel out the 4 and the 2 because they got. Well, no, you can't. You can only cancel out one of them. The 4's cancel out the 4ax.
Okay. You're right. These two cancel out.
Yeah.
And actually, that's why I thought you were just doing this to make it look more. Yeah, but here you have one positive, another positive, and two negatives. So those all go. Okay, so everything here goes that we, not quite everything. All that you have left is 2a e to the x is equal to e to the x, which means 2a is equal to 1.
A is equal to 1/2.
1/2. Perfect. So there's your undetermined coefficient. You just determined it. A is equal to 1/2. And everything else is gone. So yeah, you feel really sweet and good about it. Okay? So now we write down our,
Do you plug it back in?
yeah, to the particular solution that be 1/2 x squared e to the x. Okay? So your general solution would then be C1 e to the x plus C2 x e to the x plus 1/2 x squared e to the x. Notice the particular solution does not have an arbitrary coefficient. The complementary solution does.
The particular equals the y of c plus yp.
Yeah.
Okay.
It's all your yp's added together. You only had one in this case. All right. That was example 7. Okay. Yp is a x squared e to the x. Solve that and you get a, so yp is equal 1/2 x squared e to the x. Okay. Now, pretty close to where we usually take a break. You want one?
Yes.
I think I need one too. So we'll pick up next time when we come back from break at suppose blah, blah, blah. Okay, so I'll leave that in place. So let me put this on pause. That was our example 7. We took it a further step than they did. They just went for the particular solution. So we're going to start out in the paragraph right below example 7 before you get to example 8. So let me erase. Can I go and erase this? Okay. All right. Now, suppose again that g of x consists of m terms of the kind given in table 4.4.1, that big old long table for the different g of x's. Okay? And suppose further that the usual assumption of a particular solution is the sum of all those various particular solutions. That your y sub p, just like we just did, y sub p is equal y sub p1 plus y sub p 2 plus y sub p 3 plus dot 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 plus y sub p sub n. Lots of subs and subs and subs. Okay. Now, these are the trial particular solutions corresponding to those terms. Under the circumstances described in case 2, we can make up the following general rule, and this is called the multiplication rule for case 2. I can't write today, goodness gracious. Okay, now remember case 2 was when you did have the form of the particular solution is a linear combination of all the linearly independent functions that are generated by the repeated differentiations of, no, I'm sorry, that's case 2. I'm sorry, I was reading the form rule for the case 1. The function in the assumed particular solution is also a function of the associated homogeneous differential equation. So what do we do if you have that case? Well, here's what it is. If any of the y sub p any of the y sub p's, i's, where I goes from 1 to n, or whatever, okay, contains current terms that duplicate terms in y sub c, which is your complementary solution, then that y sub p y sub pi must be multiplied by some power of x, x to the n, where n is the smallest positive integer that eliminates the duplication. Okay. All right. I guess he's got the book, so I'll let him look at it if he needs it. Because I believe we're going to need all the room we can get for example 8. So I'm going to erase this, if that's okay. Do you understand what that means? Yeah. Got it. Okay. Here he is. Well, okay. Well, now I'll excuse you for coming in back late. Okay. Good to hear.
I did your boy Daniel.
What's that?
I did your boy Daniel Bernoulli.
What about Daniel?
I wrote about Daniel.
Oh, okay.
I kept on talking about him.
Yeah, okay. Fantastic.
He's cooler than Newton, though.
He's what?
He's cooler than Newton.
Cooler than Newton? How can you say such a thing? Okay. I thought you were talking about Daniel Granville for a second.
Oh, no.
Okay.
Sorry, my bad.
No problem.
I was talking about
Charles
Bernoulli,
is here.
not
Yeah, got it. Okay. All right. Good to have you. Okay, I just was about to erase this, so before I do, let's bring Charles up to speed a little bit here. What we're dealing with are your particular solutions now. You know, when you have a g of x, when you have a linear differential equation with constant coefficients, but then you have a particular, you have a g of x on the other side of the equal sign. Okay, you first deal with this side and get the complementary solution by setting that g of x equal to 0. you come up with your m squared, you know, all that kind of stuff, and come up with your complementary solution with arbitrary coefficients in it. Then for the g of x that's over there, you come up with a variety of particular solutions that will solve that, okay? And that can be one, it can be a sum of several, but they all have to be the form of a polynomial function, an exponential function, a sine or a cosine function. I think that's all of them. And then any linear combination of those or multiple or products of those. So have a whole bunch of those. So you could have a whole string of particular solutions that might work. But if any of these particular solutions here contains a term in your complementary solution, say this had a C1 e to the minus 3x, and one of these particular solutions had an e to the minus 3x in it. You can't use that because that's already one of these. So if you did have any that contains a term in the complementary solution, then that particular solution that is the same or very similar to that one must be multiplied by some power of x, where that power of x is the smallest positive integer that eliminates the duplication. So if this one had a, say, e to the minus 2x and an x e to the minus 2x and an x squared e to the minus 2x, but you wound up with an e to the minus 2x here, then you have to use x cubed. The smallest n that will not duplicate one of those. Okay? And that's where we are heading for example 8. I was just about to erase, so I'm glad you came in before I erased. All right. All right. Here's your initial value problem. Solve y double prime plus y equal 4x plus 10 sine x given that y of pi is equal to 0 and that y prime of pi is equal to 2. Okay. A little bit of a timeout here. This is an initial value problem. Why? So both of these conditions are evaluated at the same point. Pi. If one of these had been y of 0, the other had been y or prime of 0, y prime of pi, that's a boundary value problem. That's a different issue. They have to be evaluated at the same place. Your maximum derivative here is the second derivative, so you've got to have two initial conditions. Never have one that's the same as the max, but y and y prime, that gives you 2, you're fine. Okay, if this max had been y, the fourth derivative, then you need 4 this, but it'd be y prime, y double prime, y triple prime, not y to the fourth. So, anyway, there's our problem. Where and how do we begin? Nobody knows.
M squared.
M squared. This is now what we're calling the auxiliary equation. M squared plus 1 equals 0. That's for the homogeneous case, when that is not equal to g of x, but is equal to 0. Okay? What does this give you as possible solutions?
M equals I.
M is equal to?
I.
The i's have it, no?
Is it not I?
Plus or minus I. You have to have 2.
Why is it plus or minus I?
Okay?
Oh, yeah, square root, sorry.
Yeah, all right.
So then it's got to be YC.
The y sub c
equals C1.
is what?
C1.
C1.
E to the X.
Where'd you get that?
I thought we plug in. Oh wait, no. We did the cosine graph.
Oh yeah.
Sine of x, or sine, of x plus c2 cosine x.
Okay. Now, if you weren't here for the earlier, this obviously has no real solutions, and it has, since these are all real coefficients here, and all integers, okay, then your imaginary or complex solutions are going to come in complex conjugates of each other, and that certainly is. And actually what that is 0 plus I, 0 minus I, right? The real part is 0. And when you have this kind of situation, your complementary solution would be e to the real part, let's call it, they call it alpha x times C1, and it doesn't matter which you put first, I'll go on and do it like he did, sine of beta x plus C2 cosine beta x. It doesn't matter which one you put. The book usually puts the cosine first. It doesn't matter. The beta is the coefficient of the imaginary part. Here that's 1. And the alpha is the real part. That's 0. Well, e to the 0 is 1. So you don't have an exponential part. So that's why those were left out. Okay. Just a little bit of catch up there for how that came about. Okay. Now, okay, forgot where we were here. Okay. Okay, thought they had left off something, but they didn't. Your g of x is this thing here. I'm going to write it over here. G of x is equal to 4x plus 10 sine x. Now look at this, just for a moment. Here, this duplicates that. Okay? So, when we're coming up with the particular solutions that will work for the g of x, we can't use a sine x, because that's part of your complementary solution. That's always going to give you a 0. You're not going to get the thing that you need up there. So in this case, what would be your particular solutions? Y sub p. You want to do them in pieces, or you want to do them all at once?
Pieces.
In pieces, okay. YP1. What would that be?
AX.
Second?
AX plus B.
AX plus B. That takes care of your 4x. Okay? Your YP2 would be what?
That one's going to be sine x plus 10 sine x plus 10 cosine x.
Height. Okay, no, what? Okay. I thought you were giving me an audible there. Okay. No? All right. All right. You don't use the 10. You need another arbitrary, undetermined coefficient. So let's use C. Is that okay? But we can't just do a C sine x, because that looks just like this one. So what are we going to have to multiply by? X. Cx sine x plus
C, or no, E.
Yeah, they don't like to use D, so E.
X.
Okay, that's the issue. Do we need an x there, or will a cosine x work for you? let's see, if we put a cosine x here, then its derivative would come out being just like that. So nope, we can't. We need an x there as well. Ex cosine x. Because a cosine x by itself would look just like this one. Okay, and we can't have that. So we multiply by some power of x, the lowest power of x, integral power of x, that will not duplicate one of those. So those are our two possible particular solutions. Now, you might ask yourself, why do I need a b here? Because we only have an x here. Well, any of the derivatives of this also have to take the derivative of that. You get a constant, and you won't be able to get rid of the constant because this one doesn't have a constant term in it. So you need, for polynomials, every possible term in the polynomial up to that degree. And when you have sines or cosines, you have to have sines and cosines because the derivative of sine is cosine, and if you took the derivative, you got to be able to get rid of it. Now, you may not use them all. Some of those coefficients may turn out being 0. Fine, no problem. But you have to include them in case they're not going to be 0. Okay? All right. So those are your two possible particular solutions. Let's do the general, no, let's do the particular solution. Y sub p is equal to the sum of those. Ax plus b plus cx sine x plus ex cosine x. Okay? That's our particular solution. Now we need to take the first derivative, y prime particular, and that would be what? You tell me. A plus
that one's going to be cx
cx cosine x, I agree, plus c sine x, good old product rule, plus e cosine x minus ex sine x. Okay, everybody agree with that? All right. And there's not a single term you can combine. But we need y double prime as well. So y double prime, y particular double prime, would be what? Help me, somebody.
Sorry, I'm trying to think of it. Minus c sine x. Or cx sine x.
Cx sine x, okay.
Plus c cosine x. Minus plus c cosine x. Minus e sine x. Minus e sine x. Minus ex cosine x.
I think we got them all. Now some of these can be combined, like those two and these two. So let's shorten it as much as we can. Y particular double prime equal to minus cx sine x.
Plus 2c.
Actually, yeah, okay. Plus 2c cosine x minus 2e sine x minus ex cosine x. All right. Now, we take this and plug in for this one. It's going to take most of the board, okay? Minus cx sine x plus 2c cosine x minus 2e sine x minus ex cosine x. That's your y double problem. Plus your y particular. That was it right here. So that's just going to be plus ax plus b plus cx sine x plus ex cosine x. And we want that to equal 4x from up here plus 10 sine x. Oh my goodness. Well, it's just a lot of terms. Okay. So, let's first get our x sine x terms. That's going to be a minus c plus c, and that equals 0. Okay? That was easy. Good. Those add to 0. All right? They better, because we didn't have any x sine x's over there. Let's see about our cosine terms. Here's a plus 2 cosine x, 2c cosine x, a minus, oh, that's x. Oh, no. Uh-oh. It looks like c is going to have to be 0, doesn't it? Unless we made a mistake somewhere, that c is going to have to be 0, because there's only one cosine x term here, and there's no cosine x terms there. So let me make sure I haven't made any dumb mistake here. Our c was this x sine x term, right? There's in the book, that was the e term, and their e does turn out to be 0. So that's right. So our c is 0. So we got that. C is equal to 0. Do you see why? Here we only had one cosine x term here. This is an x cosine x here. There's an x cosine x. Okay? That's the only one, so that means 2c has to be 0 because there's no cosine x term there. So c has to be 0. Okay? So let's go to that, to the sine x terms. Here we have a minus 2e. That has to equal 10, right? Okay? So that means our e is equal to minus 5. Divide both sides by minus 2. So our e is minus 5. Okay? So those are taken care of. Now let's do our x cosine x terms. There's a minus e and a plus e. Those add to 0 by themselves, fine, good. We didn't want them anyway, okay? Then we have our ax term here, and here we have a, that's the only x term here, is equal to 4. There's the only x term there, so a is equal to 4, okay? That's taken care of. And I think we've taken care of, oh, whoops, whoops, here's a b. And there's no b over here, so I think we determined b has to equal to 0. Okay? And let's see if that's what they got. Yes, it is. Look at that. Okay? So let's write down what our particular solution is from up here. Y sub p is equal to a, which is 4, x plus 0. There is no 0. There is no b there. And our c was 0. so there is no C term there, plus, plus our E is a minus 5. So that's not a plus, it's a minus. Five x cosine x. There's our particular solution. Okay? Now, let's write down our general solution. Y is equal to our complementary solution, C1 sine x plus C2 cosine x plus your particular solution plus 4x minus 5x cosine x. All right. Now, unfortunately, since we have initial conditions, we also need to know what our y prime is. Okay? So let's do our y prime. What would that be?
It would be C1 cosine x minus C2 sine x plus 4 minus, actually no, plus 5x sine x minus 5 cosine x.
All right. Now I think I'm going to need to erase some stuff.
Yeah.
So y'all have a preference of what to erase?
Do we need that big long equation still?
No, we don't. You want that at the very bottom?
Yes, sir.
Down
Just
here?
Put it under that y prime.
Okay. I sure hope we don't.
So much
All right. How about the y to p double prime? You want to get rid of it too?
Yes, sir.
Okay. No, it isn't, but it's too late now. Okay. All right.
Alright, negative C1 sine x for y double prime. Are we doing y double prime?
No, we don't need to do that. The only reason we did these two is because we need to plug in our initial conditions.
I thought we had the,
No. We don't trust everything we've done is true so far, so let's get our initial conditions.
Plug it in now?
Yeah, so let's plug in y of pi, because this is y of x.
Yes, sir.
This is y prime of x, okay? So y of pi would be?
0? Or wait.
Okay, that's going to be 0, and that's equal to?
C2.
Say again?
C2, plus C2.
Okay, over here, yeah, okay, because sine of pi is 0, you go straight to the second one, C2, because cosine of pi is?
1.
Negative 1. Cosine starts at plus 1, pi has a 0, pi is negative 1. Okay. So it's minus C2, right?
Plus 4 pi.
4 pi.
Minus.
Plus.
5 pi.
5 pi. Got it?
Yes, sir.
So what does this add to?
Negative C2. Wait, C2 equals 9 pi.
Okay, C2 equals 9 pi. All right?
I don't know if we can simplify it anymore.
That's about as simple I think we can go. Okay? And how about our y prime? No, not double, single prime at pi. And that's going to be?
Negative C1.
Okay, negative C1.
Plus 4.
Plus 4.
plus 5.
That's it.
Where do you get plus 5?
So minus 5 cosine x, you plug in, you get cosine of pi.
Oh, okay, okay. All right. Because the sign here was 0. Got it. Okay. And what does this tell us?
C1 equals 9.
C1 is equal to 9. So now we do our solution, our general solution up here. Let's repeat that. And we have y is equal to our C1, 9 sine x
plus 9 pi cosine x
plus 9 pi cosine x
plus 4x
plus 4x
minus 5x
minus 5x cosine x. There's our general solution. And let's see what they got.
And do we plug in the initial conditions at all, or no?
Do we plug in what?
Do we plug in the initial
No,
conditions?
we use the initial conditions to get our C's, C1 and C2.
Yes, sir.
Okay, so let's see how the book wrote it. And you see, they chose different values and stuff, but it still worked. Well, no. Don't tell me this.
We did wrong.
The 9 pi cosine x works. They got 7 sine x. We got 9 sine x.
Is it on the y? Do we mess up on the y or the y?
Y prime looks like it. Okay. There you get minus C1 plus 0 plus 4.
Well, it looks like they plugged in C2, but they got 7 for C2.
Well, okay. What their C2 is our C1. See,
Okay.
I went with you. So let's see. Okay, we got C2 cosine pi.
Oh, I see where we messed up.
Okay, tell me.
Y prime of pi is equal to 2.
Is equal to what?
Equal to 2.
2, that's it.
So the y is equal to 2. So
Is equal to 2, that's it. So C1
is equal to 7.
would equal to, 7. That's it. You're right. So that would be right there. All right. All right, good deal. Okay. So 9 pi cosine x plus 7 sine x plus 4x minus 5x cosine x. Got it. All right. All right. Let's move on to example 9. Okay? Any questions on this before we leave it?
Yes, sir.
Pretty good review of just about everything we've done. Okay? So let's do example 9. Solve this. Y double prime minus 6y prime plus 9y is equal to 6x squared plus 2 minus 12 e to the 3x. All right. Make sure I copied everything right. I did. Okay. Where would you begin?
M squared.
This is called the auxiliary equation. M squared
Minus 6m.
minus 6m
Plus 9.
plus 9
Equal to 0.
equals 0. Because you use that in the homogeneous case where you ignore the g of x here and put a 0 in its place.
M minus 3. M minus 3.
M is equal to what?
M minus 3.
M minus 3 times M minus 3. Is that what you're saying? Yeah. M minus 3.
M equals 3.
Okay, so M is equal to 3.
So then your y of c equals
Y sub c is equal to
c1
c1
e to the 3x
e to the 3x
plus c2
plus c2
xe 3x.
x e to the 3x. Okay, anytime you have a repeated root here, then again we introduce another x. Okay, so this would be, where this comes from is the assumption that whenever you have a linear differential equation with constant coefficients, your assumption for the homogeneous case is that y is equal to I can't write, e to the mx. And that's how you came up with that solution, okay? So you see your y prime would have been m e to the mx, and y double prime would be m squared e to the mx. So if you plug that in there, that's where your m squared minus 6m plus 9, the e to mx, you divide out, and that's where you get your auxiliary solution, auxiliary equation. But then when you factor this, you get the same one. So you have to have two. So the first one will be e to the mx, but the next one will be x times e to the mx. Because you have the same m, you couldn't use 3x twice, because that would only be one linear arbitrary solution. Okay, you need two. So there's your complementary solution. What's next? What's next?
Oh, we're trying to solve the y
sub p, and what would that be? You want to do it separately or together or what?
Separately, please.
Okay, so yp1
ax squared
plus
bx
plus bx
plus c.
plus c. Now that's for the first two terms here. This is the polynomial part. Forget about that for the polynomial part, but you have to account for every term. So you have to have an undetermined coefficient for the x squared term, the x term, and the constant term. Okay? So we've got yp1. How about yp2?
Y sub p2 equals ax.
Not a, we've already used a.
EX.
E, and you said x?
Maybe. I don't know.
No, you're right. I don't think you knew you're right, but you are.
Plus that.
You already did the one for this one.
Okay.
Now we're doing the one for that
So
one.
then just e to the 3x.
Oh, e to the 3x. So we don't need the x in there. Is that what I heard?
Yeah. That's what you heard.
Is there a problem here, Houston?
Got a space.
Huh? Oh, I did leave a space there. Silly me.
Negative 12 e c 1.
There's already an e to the 3x here.
X.
We can't use e to the 3x. There's a c1 e to the 3x. So,
X squared.
aha, yx squared.
Is
Because we already have an x there too. So yes, we need that to be an x squared. Why did I leave a space there? Okay. All right.
Why did you erase the x? How could you
What's that?
You could have left the x there and just put a squared up there.
Well, no, you told me not. Okay. All right. So what's your particular solution?
Yp equals ax squared plus bx plus c plus ex squared e3x.
All right. Now, what do we need to do with that?
Add to the yc.
Oh! These are undetermined coefficients. We've got to determine them first.
Take derivative.
Take a derivative. Right, very good. Y sub p prime would be
2ax plus b plus 2e x e3x plus 3e x squared e3x.
perfect. Nothing we can combine there, so let's go on.
Take another derivative.
What's that?
Take another derivative.
Yes. And that would be
ax, no, 2a
2a
plus
Oh,
Oh, did I mess up?
I don't know.
Oh, I didn't.
Where'd you get the 9?
I didn't do the product rule. My bad.
Oh, okay.
2EX, or no, 6EX, E3X. Plus the 9EX squared E3X. Plus 6EX E3X.
Did y'all follow all that? I think we accounted for every term. And now what do we do?
Take another derivative.
No, please not. Okay. All right. Let's first see if there's any terms you can combine here.
You can combine
These two.
yeah.
I think that's all, isn't it?
I believe so.
Pretty exciting stuff, isn't it? Okay. Okay. So we will combine that. So your y prime double prime, that's this one, that's going to be 2a plus 2e e to the 3x plus 12 capital E e to the,
3x.
no, that's x. Wait, ex e to the 3x. This is really getting ugly, isn't it? Plus 9e x squared e to the 3x. Minus 6 times that next one there. Ugh. That's minus 12ax, right?
Wait. What do you minus?
Okay, you see up here, it's a minus 6 y prime. Here's your y prime.
Oh,
So minus, that's what I'm doing. Can I?
Yeah, I guess so.
Okay, please, thank you.
Plus 6b.
Minus 6b.
Minus 6b.
Minus 6b.
Minus 12ex 3x.
Minus 12ex e to the 3x.
Minus 18.
Minus 18 ex squared e to the 3x.
That's it.
Okay, and I got plus 9 times y, so that's going to be plus 9ax squared plus 9bx plus 9c plus 9e capital E x squared e to the 3x. And that's supposed to equal 6x squared plus 2 minus 12e to the 3x. Okay, let's start with our constant terms. A 2a, that takes care of that one, minus 6b, that takes care of that one, plus 9c, oh boy, who came up with this problem? That's supposed to equal, the only constant term here is 2. Okay? Buy it? Okay. Now let's deal with our e to the x term, e to the 3x term. That would be a 2 capital E Is that it? It looks like it. So 2e has to equal minus 12, because that's that term, right? So it looks like to me the e has to be negative 6. All right, that's done. Now let's do the x e to the 3x terms. Okay, that's going to be 12e, right? Okay.
Another 12. There's a negative 12, so that just cancels out.
Okay, so those two, yeah. Are there any other x? No, there aren't. Okay, That's good because we didn't have any on that side anyway. Okay? Now we go to the
X squared.
already, okay, x squared, yeah, okay. So those go away. So this will be,
12ax.
I'm sorry?
Are we going to do the EX squared?
The EX squared term. Well, the x squared e to the 3x terms.
9e.
So it's 9e. That takes care of that one. Minus 18e. Plus 9e.
That goes to 0.
And that's all 0, which is good because we didn't have any of those here either. So those all go to 0. Now our x terms.
Negative 12ax.
Negative 12a. That takes care of that one. Plus 9a. Whoa! No, that's not right.
What about
Because
9?
that's the x squared.
Can we do the 9b?
Wait, we might get there. Hold on. Okay. All right. Yeah, plus 9b. That takes care of that one. I think that's all.
What about
And that has to equal 0.
Why's it got to equal 0?
Because there is no x term on the right-hand side.
So,
Is there?
No.
Okay.
So you're left with a 9ax squared equals 6x squared.
Yep. So 9a, I'm going to leave off the x squared, is equal to 6.
So that means a is equal to
2/3. Okay. A is equal to 2/3.
So then we plug in that 2/3 into
Right here. And we have minus 8, right? Plus 9b is equal to 0. So our b must be equal to
8 over 9.
8 over 9. These are wonderful looking numbers, aren't they?
So then we
Now let's plug those in here. And we have 4/3
minus 48 divided by 9.
How about let's doing 2/3 of 8? That would be 16/8, 16/3, right?
Yeah.
Is that right?
Yeah.
Plus 9c is equal to 2.
So then we
Before I do any more, let me make sure these numbers aren't too wacko.
12 over 30.
Which one were we doing? Follows A is equal to 2/3. I think that's what we got. B is equal to 8/9. We got that one. C is equal to, okay.
C is equal to 2/3.
You got it? Did you work that out? Okay. So C is also equal to 2/3. And E is equal to minus 6. Yeah, we already got that one. So here we have that, that, and that.
Booyah.
And that's what they got to, I think. Yes. So now I think we're ready to write down our solution. So can I go up and erase right here? These actually almost turn out being fun, don't they? Long and tedious, but say, yes, they're fun.
It's fun when you do them.
It's more fun when I grade them, okay? No, I'm just kidding. All right. So what's your y? What's your y? The general solution is your, and we don't have initial conditions, so we can't eliminate the arbitrary coefficients, is yc plus yp, and this will be c1 e to the 3x plus c2x e to the 3x plus 2/3 a squared plus 8/9 x plus 2/3, that's the C part, minus 6x squared e to the 3x. Let's see, C1 e to the 3x plus C2 x e to the 3x plus 2/3. How did I get an a square in there? X squared. Duh. Y'all let me get away with it. What are you thinking, huh? X squared plus 8/9 x plus 2/3 minus 6x squared e to the 3x. Done. All right. Wasn't that fun? All right. Unfortunately. Oh, yuck. Okay. Just when we were beginning to have fun. Okay. So, that's it for the course. Sorry we didn't get to variation of parameters. That was going to be the very next thing we did, but we didn't get there. If you need to do some homework exercises, any of the odds 1 to 25 that are in the back would be good. Any of the odds 27 to 35 would be good. Either 37 or 39 would be good, and 41 would be good. Any of the discussion problems you see back there in the back, you can look at those as well. There's even a computer lab assignments, and I know some of you love MATLAB and want to do it there. So, knock yourself out. Did all of you get the test? Yeah, the final. Okay. Let me go over what you're responsible for and what you're not. Okay. I've got to find my copy of it. Okay. Question number 1. You can do all A through H parts of that. All you're doing is determining if these are independent or dependent on each other. Okay? So 1, all those pieces there. Number 2, you can do the undetermined coefficient. All you do is answer yes or no for those undetermined coefficient. We didn't get to do variation of parameters. So you can leave those blank. If you want to try to figure them out, they could be bonus. If you leave them blank, they don't count against you. If you get them wrong, they don't count against you. If you happen to get them right, they could be bonus ones. Okay? And then 3, 4, and 5. Where is 6? There is no 6. 3 through 6. It's 3 through 5. In problem 3 through 5, find the general solution.
Is that just doing M?
Well, 3 and 4 would just be dealing with M's, but number 5 is going to be the M's and the Y sub P's. Isn't that fun? Okay.
That's awesome. So
okay. So basically everything except variation of parameters. And you can do those if you want to. Okay. Now, some of you came in a little later, and I may have said something incorrect earlier. Let me review when I'm going to be here and when I'm not. I'm here on this campus today until 2 to 2:15 because I've got an eye appointment across the street here at UAB West. Last time they kept me for about 2 hours, so I may not get back to have any office hours, or if I get through early, I might be back for office hours then. But I've got to leave by 4:15 because I've got a class over on the, no, I'm sorry, 4:15, because I have a class over on Birmingham East Campus at 5. So I want to get there in time to set up for it, if I can get out of the doctor's appointment in time. Okay, so I'm here until, guaranteed to be here until about 2 or 2:15. Then I'll be at the doctor's appointment and then probably heading to the Birmingham East Campus. Tomorrow, that's exam day, so I'm in the office 8 in the morning, unfortunately only till about 12:30, because they called it a committee meeting that I'm a member of on the Birmingham West Campus, so I have to go over there. That starts at 1, and most of the time on these committees, they've been going about 2 hours, so I'm going to guess I'll be in the meeting from 1 to 3, but then after I get out of the meeting, 3 or whenever it's going to be, I'll stay over there and just do office hours in B122. That's the academic building, room 122. I'll be there from when I get out of the meeting, say 3 o'clock until 6 o'clock, whatever. All right, that's tomorrow. Thursday, no classes in either. We don't meet Thursday, but I'll be here from 8 in the morning until about 4 in the afternoon. At 4 in the afternoon, I'll get ready and go over to pick up the test over there. But all I'm doing over there, well, this is Birmingham East Campus, and this is in the Ethel Hall Health Professions Building on the East Campus, and I'm in room 214. And I'll just be there as the students come in and turn in their tests, you know. So I'll be there from 5, little before 5 until probably 6:30 or later, okay? But this I forgot to tell y'all before. We go back to a 5-day work week this week because Friday is in August. So I'll be on the Birmingham West Campus, B122, from 8 to 12. So that gives you one more day to work on things and turn them in. But you have to bring it there. Don't slide it under my door here. I'm not going to be here, okay? So the last time I'll be here will be Thursday about 4 o'clock, okay? Anytime after that, you slide anything on my door, I won't see it until fall term, okay? That'll be an incomplete for you, okay? So anytime after 4 o'clock on Thursday, catch me at the Birmingham East Campus, Ethel Hall Nursing Building or Health Professions Building, room 214. I'll be there until 6:30 on Thursday. And then on Friday, Birmingham West Campus, B122, I'll be there till noon. Not much past noon, guaranteed, okay? All right, any questions? You got your test? Have you done student course evaluations? You have, good, all right, excellent. And then enjoyed having you in class. Been a good class, and those times I got to see you. Okay, but y'all have worked hard, done well. Good deal. All right, sock it to it. That's it. Any questions?